So, okay, so my name is Dьюлы Катоны. Yeah, in Hungarian, the accent is always on the first syllable. So it's Katona, but I introduce myself in America, Katona, because they don't understand here. This way, I am from Hungary. And I will give a little short introduction to what is called extremal set theory. The whole thing started actually in number theory. German mathematician Sperner asked if you have an integer which is which is square free. So when you take this expansion, every prime is only one, so there is no square or third power here. And his question was that how many divisors of n can be chosen in such a way that one divisor doesn't divide the other one. And if you think 2 seconds, then you understand that this is actually nothing to do with number theory. Here you have a set with the elements, these primes, and a divisor is a product of some of them. So this is a divisor when you multiply some of the p's. And so you have to choose many subsets in such a way that this condition means that this is forbidden. Because if this divisor is a product of these primes and the other one is a product of these ones, then this will be a divisor of D2. So this is the question, maximum number. Yeah, I will always denote an element set in this way, which actually means ordered. But I will not use the fact that it's ordered. It's only an element set. And family of if its subsets, this is a family, and now we exclude this one. So we say that if F and G are members of this family, then F is not a subset of G. And the question is, to make it more precise, more clear, this is the question under this condition. So n is given and this condition. If you don't know the theorem, then can you give me a suggestion? It you don't have to give the largest one, just one family which satisfies this one, and fairly big. Oh, so you know the answer immediately. Okay, so it's obvious that if you take all k-element sets, a k-element set cannot be a subset, proper subset, because they should be different, of course. Cannot be a subset of the other one. So an easy construction is to take all k-element subsets, and then you have this number. And of course, its maximum is when you take all n-half element sets. So theorem is that no, I don't repeat. I'm sorry, I don't repeat the condition. So under this condition, so this is the largest, what the colleague suggested. So here we showed that it is good. We can have this many, but Sperner claimed that you cannot have more than this one. And I will start with the original proof, which is not the simplest one, but it has some ideas which good to know. First, I introduce a notation. First, before that, another notation. So Fk is the k-element members. So formally, and I introduce the shadow, which consists of the sets G such that it has k minus 1 element, and there is an F in the family such that G is a subset of F. I will show some pictures to make it more clear. So looking at this, you have many k-element sets here, and delete elements one by one to get k minus 1 element sets in all possible ways. And these k minus 1 element sets are elements of the shadow. It's a family again. But so I will use this picture to illustrate situations. where this is the empty set. Here we have a one element sets, here we have the two element sets, here we have the total underlying set and minus one element sets, and we have connections. It's obvious which way. So one element sets are all connected. It means that subset, but only one element difference. And so in this picture, we have the k element sets sitting on the kth level. And the shadow is, if you take all things below it on the k minus first level, and yeah. So one explanation why this is called shadow, here you have the sun and it's projecting the elements to this level. So what is the minimum of the shadow, the family of shadow, if we know the size of the family? From each k element set, we can delete every element. In this way, we obtain k minus one element sets. But in this way, k minus one element set can be obtained from many sets. But which ones? We add now one element, and those are the sets which can be can create this k minus one element set. So here we have this many. So this is the worst case when they all coincide. So we divide it by the largest possible number here. Is this clear? Because it can be told in a more clear way with double counting. If you count the pairs, k element set and subsets. But I hope this is clear. So we proved it. So Sperner's idea was that let capital K be the maximum size in the family. So we have a family satisfying these conditions. And so the largest sets. So in this picture, they are on this level, and we have many other ones here, but nothing here, because these are the largest sets. And so his idea to try to push down them by one level. So take a new family, f prime, take out the k element sets. This is capital K, this was lowercase k, and add the add the shadow so we delete this one and we add all the shadow members. Claim f prime satisfies, claim 1 satisfies the conditions. I think grammatically you have to say conditions, but there is only one condition, namely this one. So why? So first of all, we have to show this trivial thing that we don't repeat sets in this way. So no member repeated, which is obvious. Oh, here. I don't need another picture. So can it happen that we push down this here and the set, the shadow set, is already sitting there? Is it possible? So these are in F, this is in F. This is a contradiction because this is a subset of this. And according to the condition, this cannot happen. So the first trivial part is that these sets are all different. But the somewhat less trivial statement is that we don't have inclusion in the modified family. So how could we have one? These two cannot be in relation because we didn't change anything. Oh, no, not even here. So these, nothing happened to them, so it cannot be a problem. So the only new elements can cause elements in the shadow. And they are the maximum after this change. So the only thing what can happen that this set is a superset of some other set in the family. But if this is a superset of this, and this was obtained by this, then in the original family, when it was not pushed down yet, this pair was contradicting the condition. So this is what we obtained. And but what happened with the size of the family? That's the next problem. So claim 2 before I say there is an inequality between these two. Oh, I'm sorry. Előadok Moszkvába, szia! So I better show the proof and then I give the inequality. So the size of f prime is equal to the size of the original family minus the size of this level, and we added the shadow. So now I forgot, but it's not too late, is to suppose that K is more than n². Then this coefficient will be, actually, I think it is more than 1, right? Is it? Okay, I check it. So more than ½, then we have only the inequality. Because I suppose here only that it's more than ½, so it can be m plus 1/2. And so then continue this inequality here. And this is more than ½, so it will be more than fk. So this is more than fk. No, somewhere I lost the inequality. Yeah, here. Is it clear? I replaced this by this, what we obtained from the condition that this is more than fk. So what we obtained is that the new family is at least as big. It is a good family again, and its size is bigger. So we repeat it. You remember the theorem, I hope. So we started from k, the kth level, and we pushed down by 1. We obtained at least this big another family satisfying the conditions. So we can repeat. If n is even, then we can push down everything to the middle. So we have a bigger or equal family satisfying the conditions, and everything is here, and n is odd, then it's a little different, because we can go even a little bit down. So to this level, because when k was n plus 1 over 2, so when we were in this level, we could also push down. So we know that in the theorem, these can be supposed, because we are looking for the maximum, and we obtained bigger and bigger ones. And so if we find the largest one among these, it will be, of course, larger than the original one also. So what we want to obtain in the even case, that this is the largest one only. So all middle ones. So what should we do now? Question to the audience.
With the small sets.
Sorry?
Maybe we should push up the small sets.
Yeah, this is one idea, that we repeat everything, pushing up from below. But it's easier to say that we take it upside down and then repeat it. Because if G is a subset of F, then the complement is a subset of the complement of F, so it doesn't change the conditions if we take upside down. So we take the complement of every member. Then we obtain this one. Clear, it's the same problem, to maximize this or this. And about this, we know that we can push down everything. So we arrived to this family and choose n², and all the other ones are smaller because in the steps we didn't decrease it. And in the case of odd, then we have now this situation, and we can push down here, or we could also do pushing down here, because it is the same size, this level and this level. Let me note that in the case when n is even, then in each step we have a strict inequality. So when k is more than n½ plus 1, so it's above the middle, then we have a strict inequality. And strict inequality here, so we increased. So we proved, but additionally we obtained that when n is even, then is this clear, this notation? So all n½ element sets of the n element set. This is the only extremal family. In the case when n is odd, then this cannot be said, because between the two middle levels, you get the same number. So we have an equality actually in this. I mean, yeah. So we cannot say that it's bigger. And of course, this is good, but it's not clear if we can push down and not everyone. So it's still not clear if it can be a mixed family between these two levels. But later I will prove, using some other proof idea, I will prove that this is impossible and the two full levels are the two extremal families. So why I showed this complicated, relatively complicated proof? Because this concept of shadow is very useful. There are many applications and theorems about it. So it's good to remember that the shadow. And this is a basic idea in combinatorics, that you make a transformation, and if you want to look for the maximum, then the transformation makes the family or graph or anything else bigger. And then you arrive somewhere, and then it's easier to prove that this is what the maximum is there. So this transformation idea is very important, what we did here. So, second proof. Yeah, before I show the second proof, you remember what was the original question of Sperner, this number theoretical question. And when it's a square-free number, but you can ask also for any integer, and it is generalized for that case also since then. Second proof. I call it chain, which is Ci is an I-element set, but in the picture it means that we start with the empty set and one-element set, two-element sets, and so on up to here. So in other applications, it's sometimes called full chain and all kinds of names. If you want to distinguish, we could have, and later I will have, I will have chains where we don't go from the beginning to the top, but here I called it only a chain. So what is the number of chains? So C is the no, I don't need this notation. Anybody has an idea? You know? Tell me.
Do you want to show that number of
Louder, louder.
do you want to count the number of anti-chains, not each number?
No. Number of chains. No, it's different. So how to count these things or these things? N factorial, yes. Because what we do, we started from the empty set, and then we take a one element set, and then a 2 element set, and then a 3 element set. So always choose another one. So actually, we make an order. So this is an ordering of the ground set. So this is the total number of chains. And now the number of chains through a set F. So we fix an element here. So F is somewhere here. How many chains we have which go through? So everything must go through. If the size is k, but I better write in this way. Why? Because so now we have this set F here, and we start inside because we have to arrive. Increasing, we have to arrive to this one. So obviously, we arrive this many times to here, and then continue outside. So the number of elements is this, n minus f, size f, and we order them again. So now add them up for all members. So this is a family satisfying Sperner's condition. Oh my God, I didn't write his name. He invented this proof. 66.4. Now I am in trouble. Either 64 or 66. So what happens if we add them up? Could we count one chain twice? So if there were G and F, so here we took the chains going through G, and then another term, number of chains going through F. If they coincide, then it means that we have a chain going through both of them, which is impossible, because then this is a subset of this. So the number of chains we counted here are disjoint. For different F, we have completely different sets. So if we add up all of these, then we have this inequality. It can be a strict inequality because it might happen that we don't get all the chains. Now, divide it by m factorial. I make one step, two steps immediately. Yeah, in Russia you write also one like this. Doesn't matter, because in US this is one, and in Hungary this is one. You like both of them, okay. So is this clear? I divided it and took the reciprocal value, because this divided by n factorial, yeah. And now we replace every term by the smallest one, which means here we take the largest one. So the number of terms is size of f, and 1 over because the maximum of this is this. And so what we obtained is that f is less than or equal to this number. So, and so this is called the no, sorry, y. YBLM, some people call it LYM inequality, but I prefer this name, which is, this is easier to pronounce, but this is more correct. So the first person to publish this was Yamamoto. He was an algebraist, and he proved it in another context. Bolobás, Hungarian American, Lubel, and Russian mathematician. And so he had this, something like 54, and these were also earlier 63 or 64. And so he was the last one, but he had this beautiful proof. The other proofs were different, and Meshalkin already generalized Sperner's theorem. So it's a more, he had this inequality in a more general form. And so at the beginning, people didn't realize that Bolobás also proved it, because it was a lemma in a longer paper, and he didn't call as a theorem, so people didn't recognize that he proved it. So this is why LYM, and the order here is just not the years, but the pronunciation. And I like this order because we had an excellent Hungarian architect with name Ibl Miklós. So this is abbreviation of the first name. Third proof. we need some definitions. So symmetric chain is so now I don't go from, so this is also a symmetric chain, but in general it means that it starts on the case level and ends on the n minus case level. So the sizes are symmetric to the middle. So if I don't use complicated notations, I just say lemma the set of all sets, the family of all sets, can be partitioned into symmetric chains. Partition means that they are disjoint, so no set is in two chain, and every member is, and every set is in chain. So I hope it's clear what I mean by partition. So there, this must be in a chain, and because it's symmetric, so we have, certainly we have a chain like that. And then so now one element set is already settled, and for every one element set, we need a chain going to the n minus first level. So, and we have smaller and smaller chains. Yeah, a special case, this is also a symmetric chain. When n is even, then we have one element chains also. So when k is n half, n minus k is also n half. So now I am trying to prove the lemma. Induction. So if you have any doubts, if n is 2, it's true for n equal 1, n equals 1 also, but it's too trivial. So take n2, then we have this chain and the one element chain. So now suppose that C1, C2, I prefer to use this notation, the script letters for families. So these are also families. Yeah. So we can determine this R, so the number of chains, but it's not important at the moment. Is the partition for 2 to the n minus 1. And we construct the partition for 2 to the n. From each Ci, so one chain, we make 2 new chains in this one. So one idea is that I hope you don't mind this notation. This is sloppy notation, so it's union of a one-element set. So no, I better write it out. Okay, so Ck union n Ck union n minus k union n. So this is what we can do, almost nothing else, right? That we use the original chain and we extend. So this, we have this chain and we add this new point to everyone. But this will be not symmetric. So we have to be careful. So what is the size of this? This is k plus 1, and this is n minus k plus 1. So this is not symmetric, right? Because if you add these two up, then you get n plus 2. And we need n plus 1. Oh, sorry. Now I am sorry. I started with n minus 1. So it's symmetric in the original one. Then this one plus this one should be n minus 1, right? And then also here. And then the size of this is n plus k. It's still true what I know. Minus k. No, something is. I wrote here something stupid. So n minus 1 minus k. So the sum is n minus 1. And so the size of this is yeah. Oh, this seems to be good. So these chains will be symmetric. But what about this one? Here, if you add up this and this, that's only n minus 1. That's too small. So we need one more set. Here, now I am confused, I'm sorry, for a second. Help. I made somewhere mistakes with the calculation. We have to find it. So the idea is that to make this symmetric, we have to add one more set, because the sum of these two was n minus 1, and we want n. And now, if we added this one, then the sum is okay. So this is symmetric, but at this moment we have this 2 times, which is forbidden. They should be disjoint. So here we need n minus 1 minus k minus 1. So we delete the last one and add this n only to those one. And but why is this? I check it once more. So it was k for n minus 1. The problem is that I remember everything from n to n plus 1, and now I started from n minus 1 to n, and my memories are confused. So is this okay? So this was symmetric chain in n minus 1. Yes. And so we extended by one set, adding the new element to it. And then it became symmetric, because this is n minus 1 plus 1 element. So k and n minus k element. So here, this is fine. And so from this chain, we had to delete the last one. And then the previous one we have to finish, because this was already here, so we cannot repeat it. But then this is k. Oh no, it's k plus 1, and this is n minus. Oh yeah, I made a calculation mistake here. So this is n minus k minus 1 plus 1 because of this, and here this is symmetric again. So go back to this point. So we had a system of chains which gave a partition for this one. So every set was exactly in one chain. So what can we say about these ones? These chains are symmetric, disjoint, So these two are disjoint. But we make it for all CI, the all chain in this partition. So can it happen that, there is a set in two chains? In these two not, but can it happen that in CI and in CJ we have the same set? No, because these sets are all different, in different chains are different. And this was different also, we added and it will be different. And the same here. So if we have all different sets in this, and adding a new element, they will be still different. And on the other hand, if you choose any set inside, then it was in the partition, original partition. And if a set looks like this, so you add this element, then you can choose something either from here or from here, taking the remaining set, deleting this element. So this will be again a chain partition. Any question? So what? We have the picture here. So we have a chain partition. How to prove now Sperner's theorem? So in each chain, we have at most one element. Two elements would contradict the condition of Sperner's theorem. So in each chain, we have only one element. And what is the number of chains in the partition? Number of chains in the symmetric chain partition. So every chain is going through the middle because of the symmetry. Member because of the symmetry. So it's also when it's odd, we have two equal levels, then it's still true that the symmetrical one cannot avoid. So in the worst case, we have these two. In the odd case, we can have such a thing which contains both of them, but it must contain one element on this one. And every member so there is a bijection So the number of chains is n choose n half. And so this is what we wanted to prove. So the number of, for each chain we can have at most one element, so we cannot have more than the number of chains. So this is a second proof. And this one also has a reason why I showed this proof, because for some other statements, to prove some other theorems, this is more useful than the LYM. Actually, no, I am not wrong, but there are some cases when this chain partition is a better tool than the Lubel method. I don't remember the exact year, but in the 1940s. So F is a family again, but there are no R plus 1 distinct members so the condition is now that it's a chain again, but it's a different chain because they don't have to be neighboring. So we had the full chain, and it went all through, and then we had the symmetric chain. They are neighboring, but not all sizes. And here, what we forbid is a chain like that. So there are holes. So if this is forbidden, then F is at most sum of R largest binomial coefficient of order n. So the construction, that this is sharp, it's clear again, because take R levels, full levels, then you cannot have R plus 1 in this way, because we have only R. And so we want to prove now use the symmetric chain partition So what can we say now about one chain? Oh, I'm sorry. One chain. The number of elements. So number of members, say, so in one, this is one chain of is at most r. We cannot have r plus 1 in one chain because that would contradict the condition. So at most r. But here there is a little difficulty that we have smaller chains. Or the number of I'm sorry, notation is wrong. So is no, it's okay. So these were the chains, I guess. Yeah, these were the chains, and on or the size of the chain, because if the chain is small, then the condition would allow us more members, but we cannot have more than this one. So small ones are full, and the big ones we have at most k. Now we could follow this kind of calculation, but it's easier to think in the following way, that push in every chain, push the elements to the middle. And these ones are already in the middle. So the size, the maximum size is exactly this construction that you take all on this level, and of course you can express it exactly depending on the parity of n and r, but it's not important. So where to situate them to be the largest. Now, I have a couple of minutes. I sketch only one thing because I don't have enough time, but the following interesting observation is, if you exclude, so you divide the underlying set into two parts, fixed, and you allow such pairs which are proper subsets in both parts. That's possible. The forbidden is when f no, it's not the size, it's equal and or the other way around. So, no color chalk, no. So, if one set is this one and the other set is this one. So these two sets are equal in X1, but superset, one of is a subset of the other one in this part. And this is forbidden. And if you take the symmetric picture, also forbidden. But you allow this one. This is possible. And so theorem that x plus is n, then under these conditions it's still the same thing. So the condition is weaker, but the result is the same. But there are more constructions, namely if you take the complement in one side of every set, but take so you take all n-half element subsets and take the complement here of the sets, then they will be different size, but altogether the number will be the same. And because we took the complement, the containment doesn't change. So it's still true. So so the same result under a weaker condition. And I just tell how to prove, but I don't do the details. Take the symmetric chains here, and take the direct product of the chains. So one chain one chain here and one chain here, and take the direct product. I am making this picture in this way because this one level is when the sum of the sizes are fixed in the chains, and because they are symmetric, this will be also symmetric. So now we have such a partition of the direct product. Difficult to make a picture. So where these are all symmetric, and if you prove that in this one, again, of course, you cannot have subsets. So this will be a subset of this, because here increase. And so in this problem, you solve again what is the maximum without this, and it's easy to see that the middle size is the best, which is this is actually trivial because so the maximum number could be the smaller size of the rectangle, and you can do it in such a way that you take in one level. And so if you go back to the original one, you get that you cannot have more than, in every one you take the middle one, and it will be adding up to this number. Okay, thank you for the attention.